During today's session, I'm going to be exploring the atomic nucleus and considering how we can identify the actual size of the nucleus, the mass of the nucleus, and how it also has energy levels befitting the quantum world. So first of all, I'm going to take you back in time to both an experiment which took place a long time ago and some experiment you were probably made aware of earlier in the course. And that was going to be Rutherford's experiment looking at a thin gold foil. As you remember, Ernest Rutherford and his team decided they were going to fire some alpha particles at a thin gold foil, only a few atoms thick, to try and find out the structure of the atom. At the time, the plum pudding model was thought that electrons were spread evenly through the central nucleus area, and what would happen is that none of the alpha particles would be able to get through, and all would be generally reflected back again. Obviously, what we found out was something very, very different. Most of the alpha particles went straight through, some of the alpha particles were deflected through large angles, and a very few alpha particles were reflected straight back again. This was a seminal finding because it showed that an atom is actually largely made up of space, of which where the electrons are found, and a small central nucleus. Now, the reason I bring you back to this experiment is actually because of section 3. So finding 3 there, a few alpha particles reflected straight back. This finding allowed some more detail to be used to identify exactly what the radioactive nucleus was. So I'm going to look at this a little bit more detail now. So if we have a gold nucleus and we have an alpha particle which is coming in and then at some point is stationary, then it bounces back again and reflects. So this directly hit nucleus and bouncing back must have a point or when it becomes stationary. Now this is useful because the initial energy of the particle must be equal to the electric potential energy of at this point in time, because of the conservation of energy. So all of the energy must be balanced out at that moment in time. If we think about that, it allows us to estimate the radius of the nucleus. So the distance d can be estimated. We can see that there's still a gap there, but we're getting closer and closer and closer. So let's go through some maths now. Electric potential at the stationary point. Okay, so that is going to be, the electric potential is going to be K times capital Q times little q divided by d. Now, we recognize that one of those charges is going to be the gold nucleus, so we've got the atomic number multiplied by electron charge, and we also have my alpha particle coming in, which has obviously the equivalence of 2 electrons charge. Now, if we put those values in, we work out the electric potential at the stationary point is going to be 2 times z times the electric charge squared divided by the distance between the stopping point and the center of the gold nucleus. Now, due to the conservation of energy, remember we're going to recognize that the original kinetic energy of the alpha particle is going to be equal to this electric potential. Therefore, we can rearrange this to find out what d is, the distance, which is going to be the radii of our nucleus. So, assuming we know the kinetic energy of the alpha particle, in this case I'm going to put it in as 2.0 mega electron volts, and the gold nucleus has a atomic number of 79. This gives us a final d, a radius of 1.1 times 10 to the minus 13 meters. Now the big thing to notice here is that the higher the incoming energy, the closer we can get to the radius. So it means the more effective a measurement we're making. But still it's a suitable estimate of the radii of the nucleus. So that's the radius. I said I was going to talk about the size of the nucleus. Now I'm going to talk about the mass. Nuclei have energy levels just like electron energy levels in some respects. It means that at different energy levels, the likelihood of radiation being given off, so we've got alpha and beta and gamma radiation given off, it appears when looking at them they have alpha and gamma radiation produce radiation of certain specific energies. So these are discrete energies which indicate that the nucleus has energy levels. So when the nucleus's energy levels drop from one to another, then a specific gamma radiation comes out. So that crucially shows how there's a quantization of the nucleus. And that is my overview of the nucleus and what we can find out about it. We're going to talk about beta emissions and some of the issues to do with them in another video.